G'day aspiring engineers. This video is a demonstration of virtual prototyping. I'm halfway through designing a pottery kiln and I'm doing that design in Autodesk Fusion. But the virtual prototyping, I'm not doing in Fusion, I'm doing it in Solid Edge instead. Now don't get confused, it's not SolidWorks, it's Solid Edge. We'll talk more about that another day. And did you notice that this is not the Fusion logo? That's Solid Edge. But we'll talk about all of that in another video. Today I just want to introduce you to the simplest possible kind of engineering simulation. It's called linear static analysis. And that's by far the majority of all product design simulations that you're called upon to do. Between 70 and 90% of all simulations is linear static analysis. So you've heard of CAD, CAM and CAE. Well, CAD is computer-aided design, CAM is computer-aided manufacturing, and CAE, that's computer-aided engineering. Also known as simulation, product development, virtual prototyping. It's where you have a model and you know how they crash test cars? Well, when they do the crash testing, they've already done multiple experiments in the computer where they smash that thing into all kinds of obstacles and walls and stuff. They're doing buckling analysis and all kinds of dynamic and complicated analysis. But eventually, they're required by law to actually build a prototype car, a physical one that costs $1 million or more, and put crash test dummies inside it and crash it against a wall just to prove that all the design simulation work and all those virtual prototypes and the experiments that they've done in the software are validated and trustworthy, and so they can actually be confident that when they sell it and Mrs. Smith is driving it and has an accident, that it's going to behave as it's predicted and it's going to be up to standard. Okay, so I'll just walk you through this and I'll give you a bit of an explanation about how I set this up. And here's the model that I created in Autodesk Fusion. And like I said, it's half finished. But let's go and have a look. This is a downdraft kiln made out of fire bricks. And you can see that it's raised up to a comfortable working height on a welded steel frame. Now this is a hobby project, and so it has to be cheap to build, and so here's my first question. Just how strong does this rail have to be? You can see that it's got several angle iron joists sitting on top of it, and above that quite a lot of fire bricks sitting on it, so there's a bit of weight there. So it's RHS tube, that is rectangular hollow section, 50 by 20 by 2.5 thick. Now I'm going to have to buy this RHS, and so what I need to know is what is the smallest cross-sectional area that I can get away with here. What I'd normally do is set up a study, an FEA study in Fusion, but can't do that now that they've hobbled the personal use license. They've taken out the finite element analysis possibility. So here I am in the free version of Solid Edge. I'm going to do more of these in the future where I import a whole Fusion model into Solid Edge, but this one is so simple that I just modeled it up in here. And so we need to prepare for the boundary conditions, and that means the supports, the rigid supports, and the force that's acting on the middle of the rail. And so today what I've got to do is just put some sketches on those three places, two underneath and one on the top. Firstly a sketch, and then I've got to use the sketch to split the face of the top and the bottom sides of that thing. I've got this video sped up 3 times, and I'm fumbling quite a lot. It's pretty unfamiliar. You know, I was a big fan of Solid Edge about 20 years ago. It's the first CAD that I actually learned and taught. So there we are, we've finally got the faces on the top and the bottom. Split the faces on the bottom, but I had to come back and find out what went wrong with the top one. Anyway, we've only got that thing split and ready to take the rigid supports there. Now we're up to the second of 5 stages in this linear static analysis, and that is to put the rigid supports and forces on. We call it boundary conditions. So those round bubbles are the rigid supports and those arrows are the forces. And you can see I've made a mistake here. I've got those forces spread out all along the rail, but what I really wanted was for those forces to act on a face about the length of 2 bricks. Okay, finally got that working now. All right, now we're up to stage 3 out of 5, and that is to create a mesh. Normally you want the number of mesh elements to be the least number possible, because the computer is going to do a set of calculations on every single element in that mesh. And so here I am setting up the first one, and got a mesh, but then when I asked the computer to go ahead and calculate, I ran into an error message. The computation step fell over, and I was able to get a graphical representation of the problem. It's those red elements, and ended up having to repeat that whole set of steps 9 times. I was going to give up completely on the 3rd failure, but I was thinking I should go coarser to try and resolve that issue. But when I asked Google Gemini, what I did was I got my phone, got Gemini up on my phone, and I asked it to read the error message, and it advised me to go finer, not coarser, and that improved the result. And when you see these red elements in the testing step, that indicates that there's less problems and you're going in the right direction. So I just bumped it up a little bit more for the next several times until I got to the 9th one, and that was improving it gradually until it actually solved. I wanted to creep up on it so that it wasn't going to take a long time, even though this was a fairly short simulation. So that was both steps 3 and 4 repeated multiple times in that last bit, until the last one, which was actually successful. So now the 5th step, the final stage in this linear static analysis, is well, it's actually true for nearly all kinds of simulation. You've got pre-processing, that's the earlier steps, the processing, and that is the computation step where the computer is doing the calculations for you, and then the post-processing is here where we're actually looking at the colourful plots, and what you're actually looking at there is an exaggerated deformation plot. Now that's not really very much help in linear static analysis, because we really don't ever want to know about, actually bending stuff. We'll talk more about that another time. Always had an interesting time with my students on that one. But this exaggerated deformation is no use at all, and what we're going to be doing here, the challenge is to alter the display to get the useful results that you're looking for. You have to get the units right, you have to change the range of colours in the display, and you need to look for insights. Sometimes you're actually doing a section plane and cutting through the coloured results. And you're thinking about those questions that you had in mind when you first set up the simulation and started working on it. So eventually what I've done here is I've asked it to give me factor of safety. So it's related to stress, and stress is in that rail with the weights that are on there. But factor of safety means, if it's a factor of safety it's 2, it means that this part is actually twice as strong as it needs to be. A factor of 10 is 10 times stronger than it needs to be. And so we can see those values in these different nodes where I've actually pulled out the result and laid it out there. And I've made it so that the colours indicate the different factors of safety that are at play here. There's only one place where it does look like it might be a problem, but all the rest of it is well and truly, 10, 20, 30 times stronger than it needs to be. So, question answered, problem solved. Are you ready to take your CAD to the next level? Simulation can give your designs another dimension. Now, a simulation is a model that changes with time, and these kinds can answer questions that you might have. You can test your designs without building an expensive prototype. You can learn to make these virtual prototypes, so like, subscribe, and also subscribe to my free newsletter in the link down below. Thanks for watching. See you next time.